Hello everyone, welcome to Griffiths Electrodynamics. This is going to be problem 4.28. So let's take a look. This is kind of a fun problem. And so this is in the section on forces on dielectrics. And we have two long coaxial cylindrical tubes, metal tubes. One has an inner radius of A, the other one has an outer radius of B. They stand vertically in a tank of dielectric oil with a susceptibility chi sub E and a mass density rho. The inner one is maintained at a potential V and the outer one is grounded. So we essentially have a capacitor here. And it wants to know what height h does the oil rise in the space between the tubes. So this section is about forces on dielectric materials. And in this section, Griffiths does an example with a parallel plate capacitor and like a slab of dielectric material, and he calculates like what the force is. Like if I were to insert, a slab in there, what he calculates basically an expression for the force that the dielectric feels due to the capacitor, and that force is an attractive force. It tries to suck the dielectric into the capacitor in between the capacitors. So in this problem, what we have here is essentially the same setup, just in a different form. We have a cylindrical capacitor. So we have a grounded outer capacitor or outer plate cylindrical tube with and then an inner tube maintained at some potential V. And then our dielectric material that's in between the plates, right? The same thing as this problem is oil. It doesn't really matter. It's just think about the oil as just like some dielectric cylindrical material. I don't know. It's the fact that it's oil doesn't really matter here, except the fact that it's moving. It's a liquid. But the oil has a dielectric susceptibility of chi sub E, and it has a mass density of rho, which will come in later. And we want to know if I choose, an axis, Z is vertical, and it's submerged in some liquid, and it wants to know how far up is the liquid going to be pulled up due to this force. It's going to experience a force because we're basically inserting dielectric material into this capacitor. It's going to experience this force because of the relations that we derived in the section. How far up, if we define our zero to be here, I guess, right? Z equal to 0, I suppose. How far up is this liquid going to go into the capacitor due to the force it experiences? But there's also the force of gravity, right? Gravity is trying to pull the water back down. So there's two forces acting on the oil. There's the force of gravity, and there's the force from the dielectric that's pulling the dielectric into the capacitor. So anyways, let's kind of walk through this problem. How do we figure out this height Z here? Well, we should probably figure out what the force is first due to the dielectric, or the force on the dielectric from the capacitor. And then we should also probably figure out the force due to gravity. And whenever the oil reaches an equilibrium, like it's gonna get pulled up and then it's gonna stop at some point, right? When the forces are equal, when the force due to the capacitor and the force of gravity is equal, it's gonna stop moving. So we want to know, and that wherever equilibrium equalizes out at, that's the height h that we want. So in the previous section, we derived that the force is going to be related by this equation. So we have 1/2 the potential squared, which the potential is something we know. It's a given value V. I don't know it doesn't tell us an exact value, but it's just some potential V. So it's going to be 1/2 V squared, and it's going to be the derivative of the capacitance with respect to the variable in the direction that's like this way, where the direction that the dielectric is moving or can move, right? So in this case, it's the Z direction. So it's going to be dC by dZ. And so we need to find the capacitance as a function of Z effectively. And yeah, so let's figure out then, to figure out the capacitance, of course, we need to know, we know the capacitance is the total charge Q over the potential. So to figure out the capacitance, we're probably going to need to figure out the total charge Q in this, as well as the potential. But the potential is going to be slightly different because, and there's two regions here, right? We have this region here, and we have this region here. We have the region inside the dielectric and a region outside the dielectric material. So we need to figure out what the potential is in each of these regions. Well, we can do that by using the field. If we can figure out the electric field, then we can figure out the potential pretty easily. And we can figure out the electric fields pretty easily because Gauss's law allows us to do this pretty easily because of cylindrical symmetry. So in the region with air, we're gonna assume that the inner conductor has some uniform charge density lambda. So we're just gonna assume that the conductor, we obviously know it's a charged metal tube, so all the charge lives on the surface of this tube, and we're just gonna assume that it's uniform. It just distributes itself uniformly across the cylinder, and so it's gonna have a uniform charge density lambda, which is a charge per unit length. So we're gonna use Gauss's law here for the region in the air, region 1, and our Gaussian surface is going to be a cylinder. In this case, it's going to be a cylinder that lives in this top region. So it's a cylinder that wraps the inner cylinder, but it's in between the inner and outer cylinder, but it completely encompasses the inner cylinder, but it doesn't go into the oil. It's like it's going to be some cylinder that goes like this, that surrounds the portion of the inner tube that's not covered in oil, essentially. That's in the air. Now, the left side of Gauss's law is going to be the magnitude of E1 times the surface area of our Gaussian surface, which is going to be 2 pi s, if s is the radius of our Gaussian surface, times L, where L is the length of our Gaussian surface. And then the total charged enclosed is going to be this lambda, which is just this charge density times the length of, the length that our Gaussian surface is, because that's how much it encompasses. So that gives us the charge that our Gaussian surface encloses, and then we divide that by epsilon naught. So the field in the air region is lambda over 2 pi epsilon naught s, or I multiply by 2 on the top and bottom, so we get 2 lambda over 4 pi epsilon naught s. Therefore, the potential in region 1 is, of course, minus the line integral of E dot dl, and we're going to be integrating from, from B to A, from the outer cylinder, from the ground to the potential, the inner cylinder, which has a potential. So this is going to be, and this really should be E1, minus 2 lambda over 4 pi epsilon 1 over s ds, and s goes from B to A. So we end up with, this integral is just the natural log of s, and so we end up getting with the natural log of A minus the natural log of B, and that's just the same as natural log of A over B. So we end up getting this expression for the potential, and then I flip this using the minus sign, because this is the same as natural log of A minus natural log of B. You can flip those around, and then you can get the natural log of B over A if you just use the minus sign to flip those around. And this is the form that Griffiths has in his solution manual. All right, so we know the potential in region 1 in the air, but now we need the potential in region 2. Now, we're going to assume that the charge density is not the same in the oil portion, because there's going to be, it's submerged into dielectric material, so there's going to be free charges and bound charges, and so that we're going to give it a charge density of lambda prime. And we know that lambda over epsilon naught should be proportional to lambda prime over epsilon, and so we can derive a relation between lambda, the charge density in air, and the we can derive a relation between lambda prime and lambda here. So lambda prime then is epsilon over epsilon naught lambda, and then epsilon over epsilon naught is just epsilon r. So lambda prime is equal to lambda or epsilon r, the dielectric constant of the material, times lambda. Now, for the oil portion, we need to figure out the electric field, but we use the displacement field form of Gauss's law here because we're inside of a dielectric material now. So using Gauss's law here, of course, our Gaussian surface is going to be a cylinder. It's going to encompass some portion of the dielectric material here, the inner tube, completely, and it's going to be just in the dielectric itself. So the displacement field in region 2 is going to be constant, and then so we can pull it out the integral. So we're just integrating over the surface area of our Gaussian surface, which is 2 pi SL, and then the free charged enclosed is going to be lambda prime, the charge density, whatever that is, times L, and so that's the total free charged enclosed. That means that our displacement field is lambda prime over 2 pi s, or multiplying by 2 on the top and bottom is 2 lambda prime over 4 pi s. And we know that the electric field is related to the displacement field by d over e, or sorry, d over epsilon. So then the electric field in region 2 then is 2 lambda prime over 4 pi epsilon s. Therefore, using the same process as above, you can do that line integral and find that the potential in region 2 is 2 lambda prime over 4 pi epsilon times the natural log of b over a. And this is just this, you just got to do that line integral. It's pretty straightforward, the same as above, to get from here to here. So now we know what the potential is in both regions, the potential difference between the two plates. Now we need the total charge Q, right? Because the capacitance is Q over V. So the total charge, well, all the charge lives on this inner cylinder, this inner conductor. So it's going to be this lambda prime, this charge density lambda prime, that's in for the dielectric portion, times Z, where Z is whatever this height is that the oil covers, right? So it's going to be whatever this height is. We don't know what it is. That's what we're trying to solve for, essentially. But it's going to be whatever height the oil covers times of course, the charge per unit length, plus lambda, the charge density in the air region, times L minus Z. So if the total height is L of the cylinder, then we subtract Z. That gives us the remaining portion that covers the air. And then we can rewrite lambda prime using a relation from above. So we get epsilon r lambda Z plus lambda times L minus Z. And here we're just going to do some algebra. So we factor out lambda. We get lambda times epsilon r Z plus L minus Z. We factor out Z in the inner portion. So we get epsilon r minus 1 times Z plus L. And then epsilon r minus 1 is the same as the susceptibility. I have the hardest time saying that word. So we replace epsilon r minus 1 with the susceptibility chi sub e. So we get lambda times chi sub e Z plus L. And of course, Z is going to be this height that the oil ends up settling at, essentially. So now we know we have an expression for Q. We have an expression for the potential. And so we're going to be using the capacity. We're going to figure out what's the capacitance. So we're going to be using Q and V here. And we're going to be using, I believe, let me just look here. Yeah, so I guess we're just using the potential due to the free charges, because the capacitance only relies on the free charges. So we plug in Q, which is lambda times chi e Z plus L, and then V is the 2 lambda over well, hang on. So did I mess this up? Oh, no, sorry. Yeah, that's right. We have the 2 the 4 pi over epsilon naught goes to the top because we're dividing by V, and then the 2 lambda natural log of B over A goes to the bottom. So then we cancel lambdas, and we end up getting this expression and the 2 cancels with 4, so we end up getting 2 pi epsilon naught times chi e z plus L divided by the natural log of B over A. And this is the expression for the capacitance of a capacitor. So now that we have our expression for the capacitance, and it is a function of Z, right, which is what we wanted, we can now figure out what the force is on this dielectric material due to this capacitor, right? The force is on the dielectric material is 1/2 V squared dC dZ. So we just take the derivative of this with respect to Z, which is very easy, right? Because the top here is constants, this is a constant. So we're just taking the derivative of this top term with respect to Z, which is going to be just chi e. So we end up getting 1/2 V squared 2 pi epsilon naught chi e over the natural log of B over A. This is the force on the dielectric material. When we reach the equilibrium point, then the force on the dielectric is going to be equal to the force due to gravity. So the force due to gravity, of course, is the mass times the gravitational constant g. Well, what is the mass of the oil? Well, we know it has a mass density rho, and we need to know the volume of the oil. So that's going to be the radius of the oil, but the oil, it's not just, an pi r squared, it's pi times b squared minus a squared, because the oil it's not a full circle up there, right? The inner tube cuts off some area, right? So the radius, of course, goes from A to B. So the radius, this area up here ends up being b squared minus a squared, not just like an r squared or whatever. So the volume is going to be b squared minus a squared times pi times the height z, whatever that is, times the mass density rho. That gives us the mass. So this is the volume, this is the mass density, that gives us mass times g. And then we just set these equal to each other, right? When we reach the height h that the oil settles at, these forces should be equal. So the force of gravity equals the force on the dielectric. We set these equal to each other, and then we just solve for z, which I replace with the letter h to denote that this is the value that the oil settles at. So then we just solve this for h, which is just some simple algebra. So h is epsilon naught chi e v squared divided by rho times b squared minus a squared times g times the natural log of b over a. And I'm not going to do anything crazy with that. That's just the expression I'm going to use. So this equation gives you the height that the oil will settle at, which is kind of a fun and interesting problem to think about. So yeah, I hope this video helped you guys out. This was a pretty cool problem. Really like this problem. But yeah, if this video helped you out, leave a like, comment, and subscribe to my channel. As always, I will see you guys on the next video.